Now members, still we are in chemistry, and then we are going to look at now our periodic table, and then our periodic table, you know properly that you looked at the S block, then you looked at the P block, then now our idea today is going to be at what we call the transitional elements. However, these transitional elements, we are going to see them falling under what we call the D block. That middle block, remember the periodic table is having 4 blocks, so our idea here, so periodic table is having 4 blocks, is having that block there, then is having a block in the middle here, and is having a block there, then another block down here. So our idea, this one will fall under S, this one P, then our idea will be here. This one, we shall not focus a lot on that. Now, when we come now to transitional elements, we are going to focus at what we call the D block elements, or the D block what? D block series. Members, what you are going to know, there is a very big difference between the D block elements and then transitional elements. So, that one we have to master it as we are beginning. Now, you are going to discover as we are studying here that all the transitional elements are D block elements. But not all D block elements are transitional elements. That one should be clear at transition. Now, what are we meaning by transitional element? Any element can only and only be transitional, members. That is if it can form one stable ion with what we are calling partially filled D orbital. Now remember, when you go back to your chemistry, when you go back to the chemistry of Alpha-Bao, Pauline and then Hindu, you discover that when you look at the D sub-energy level, it is being occupied by 10 electrons. Being occupied by 10 electrons, it means it is having what we call 5 orbitals. That is 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Remember, each orbital is accommodating how many electrons? 2 electrons, like that. That is if we have a good spin, as Pauline and Hindu said. Now, when we talk about partially filled, it means you may have 3D1, that is partially filled. You may have 3D2, partially filled. 3D3, 3D4. Then you have 3D5. Then you have 3D6, 3D7, 3D8, 3D9, 3D10. Now I'm going to eliminate this and this. This one we shall say this one is half filled, and this one is full what? Full filled. Now if you are having now full filled, when you are forming ion which is having full filled means the all orbitals 1, 2, 3, 4, 5, 2, 3, 4. This is half filled, then and so on. Now our definition of transitional element here, we are going now to get our definition from that point of view that is only that element having partially filled D orbital. Now, if you are forming a D orbital which is having full filled, you are not transition. Take an example, we are going to eliminate scandium. Scandium, when you look at scandium, we are going to discover that scandium, like that, meaning it doesn't have an electron in it. 3 what? 3D, as we are going to see. The same with zinc. Zinc is having 3D, which is full filled. And the same with this copper 1. So we are going to eliminate scandium, zinc, and copper. Not copper 1, not being true transitional element. Reason being forming a 3D orbital, which is not partially what? Partially filled. Don't become confused by other definitions. The only definition should include partially filled D orbital. Now, when does the element become a D block, members? Remember, we have said all transitional are D block elements. The D block element is going to be that element that is filling its last electron in the D orbital. When we are going to see our electronic configuration here, all of these elements will be filling their last electron in the D orbital. Now, all of these ones which are transition are going to become D block. Why? Their electron is going to be filled in the highest energy level of 3D. Highest energy level of 3D. That one means it's having the highest what? The highest energy. Now from there, let us try to, after grasping properly the difference between the transitional elements and then the D block elements. Remember, as I'm reminding you, a D block element is only a D block if it's having or is feeding its electron, the last electrons, in its highest energy level, which is the orbital. So we are saying it's an element that has its highest energy electrons in the orbital. These ones are forming partially filled. Let us move to electronic configuration now. When you're writing electronic configuration, obviously we have now scandium having 21. 21, we are going to now to base on what we call our Fabre's principle. This man's principle here, where you are feeding electrons basing on the increasing energies on the energy level. We shall begin with our 1s here. We come now to our 2s, then we come to begin with like that. We come here, we go there, then we go there, like that onwards. So when you are feeding, we are going to begin by writing our 1s, as our Fabre was saying, and we put the 2 electrons. Then you are writing 2s, we are putting 2 electrons. Then what is the next? We are putting the 2p, and our 2p will accommodate what? 6 electrons. Remember, from the introduction of your chemistry, you said that where there is S, you put there 2 electrons. Why 2 electrons? Each orbital, S sub energy level is accommodating 2 electrons. Reason being is having only 1 orbital. Which 1 orbital must accommodate 2 electrons only. But when you come to P orbital, the P sub energy level, it accommodates 6. Why 6? This one is having 3 orbitals, like that. But each orbital we are saying is accommodating 2, like that. Don't forget that, accommodating 2. So I'm saying where it is S, we are giving it 2 electrons. Why 2? Each orbital, remember chemistry is saying you have energy level. The energy levels we have, that is KLM what? KLMN. Then you have what we call sub-energy levels. Sub-energy levels, that is the SPDF. Then you have what we call orbitals now. Here we have what we call orbitals. Now those orbitals, when you look at S is having only 1 orbital like that. Then P is having 3 orbitals. I'm representing orbitals by dividing like that. Then the D is having 5 orbitals like that. 1, 2, 3, 4, 5. But remember, each orbital is accommodating 2. So here you are putting 2 electrons inside here to give it 2. Here each box you are giving it 2. There you are putting 6. This one, each box you are giving it 2 also, like that. So there you are obtaining what? 10 electrons. Now when I talk about S, just know my S I'm putting 2. My P6, my D I put there 10. For F, which we are not going to look at, it will be accommodating 14. That one implies there are 7 orbitals, 7 boxes. Now let us come back here to our idea here. So when you are going to write here, we are going to bring now, according to our Fabao, 3S is next. Then you are putting 2, then 3P6. Then finally, we are going to put there 3D. 3D now, the 3D is going to accommodate how many electrons? We are giving the 3D 1 electron, and then 4s2. Now members, when you look at our Fabre's principle, we are supposed to put the 4s first, then the 3D last. To bring even clear the definition of D block, 3D must be last. But again, we are disobeying that part of our Fabre. Why? When we come to ionization energy, you will discover that the S sub-energy level can easily give away its electrons because it is having lower ionization energy compared to 3D. Now to bring properly the image that electrons can easily be given away from the S than the 3D, we disobey what our Fabre said here. Then instead we put our 3D first, which 3D must be last. Why am I saying like that? The 3D is having a bigger energy than the 4S. When you are calculating energy of 3D is bigger than the energy of 4S. But when it comes to giving electrons of 4S can easily be given out than those of 3D. So we shall put the 4S last, like that. But if you wrote it also like that, and you end, for example, with the scandium 3D, with the 4S, 2 and 3D 1 last. That configuration also doesn't have any problem. But now you'll be disobeying the rule of giving electrons. Now members, from there, it implies that the other elements, all of them, even when you count titanium, this structure is going to remain the same with titanium, like that. From there up to here, it's going to remain the same. Why am I saying the same? All of them are going to be accommodating 18 electrons. Count here, 4 plus 6, 10, that is 18. Meaning here you have argon. We can simply simplify everything here by wrapping up all of this one by putting what? Argon. And that argon is being occupied by 18 what? 18 electrons. Then we bring the others. So if I come here, instead of repeating all of this one, because I know what is going to happen here is going to be 3D here. 3D, 4S. Even for this one, it's going to be 3D, 4S. But the difference is going to be 3D of the other one is having what? For this one, the 3D will be having 2, and the 4S of this one will be having 2. But when this one is argon, where argon you have 18. 18 plus 2, that is 20, 22 for titanium. Then 18, then plus 3, that is 21, that is for scandium. For vanadium now, vanadium, it implies that we are having now, someone can guess here, we shall put here our 2. When you put our 2, you have 18 here. You remember we said we have argon there, argon like that. Then you are adding 3D, 4S2. The balance is going to be what? You will find that 2 plus 18, that is 20. The balance is going to become 3 there. That is what you are going to put. Then similarly, when you come to chromium, instead of repeating all of this one, you can, unless the question is saying full electronic configuration, then you bring your 3D, then 4S, like that. So when you look at chromium, remember is 24, we are going to put, for chromium, we are putting 1 here. It is only chromium and copper having 4S powered with 1. We are going to show you the reason as to why we are saying like that. Then here we shall have the 5 electrons. Then now, similarly, here we are going to obtain the same thing, like that, throughout the whole thing. What is going to change now, for manganese, for example, we shall have our 3D, 3D5, then 4S. 4S, you can see now the 4S is going to be 4S2. Then for our iron here, we shall have a 3D6. Then you have 4S, 4S2. Then look at cobalt. Look at your cobalt there, you have a 3D7. Then 4S what? 2. Then for nickel now you can also be writing there and you see nickel. Nickel we shall be having 3D, 3D8, and then 4S what? 4S2. Now for copper still we shall be having, for our copper, we shall be having 3D, but our 3D now is going to be occupied by 10. Then 4S what? 4S1. Then for zinc, we shall be having 3D, 10, but here we have 4S what? 4S2. This means what? All of this one calling it the core structure. That one we are calling it the core structure. Core structure. The structure which is stable structure, which does not even take part in bonding. That one is a core structure, and that core structure is of argon, having 18 electrons. Then the last one, this one here, the 3D4S, this one is going to work as the valence structure. This one is having electrons which are going to take part in what? In the bonding or valence shell what? Structure. So that is the 3D. Whether you have a 3D one, this is the valence structure, the other one is core structure. Now members, from there, I'm assuming you have looked at the configuration which you are writing. Don't forget this. It is only copper having power 1 at S. The remainder or the rest have for S power 2. Then don't forget that it is transition element if it's having partially filled the orbital. Partially filled, you have less than the 10 electrons. Then you are D block because your highest energy level is what? The orbital. Now let us try to look at the properties of transitional elements. Remember I've told you not all D block elements are transition, but all transitional elements are D block. Now you can only become unique. You can look at these elements we are going to talk about as transitional elements. They are different from the rest of the elements of S, and the rest of the elements of P, but they are cutting across now because they are in the middle. The S and P, then for them they are in the middle here. But we are saying not all of these elements which are in the D block, that all of them are what? Are transition. Some are not what? Transition. Now these are the properties which are making them unique to be called transition. One, these elements, the element can only become transition if it is paramagnetic. Paramagnetic is arising from what we call paramagnetism. Paramagnetism, that is the ability of being attracted by a magnet. In simple terms, you have a magnetic what? A magnetic field, or you develop a magnetic moment. Now when you look at these elements, the so-called transitional elements, which makes them different from the D block elements, we are seeing that their atoms and even their cations, after losing electrons, they are held in a weak magnetic what? Field. The weak magnetic field is arising from where? We are seeing that they have unpaired electrons. They have unpaired electrons. We have already seen, take an example, let us pick iron. Iron is 26. Iron is 26. And when you look at iron of 26, we have already said that is having 3D. When you look here, we said is having 3D. So 3D6 for S2. Now try to put the electrons of iron. You'll find that according to Pauline and Hindu, before the electrons are pairing, especially Hindu said, before you pair up the electrons, first give 1 1 to each of the what? Each of the orbital. So meaning you first give 1 1 like that, 1 1 like that. Then 1 2 3 4 5 electrons. Then there is the balance of 1. That balance of 1 will come and put it there. Then you pair up. Now look at this one, this one, this one, that one. All of those ones are unpaired. Now these unpaired electrons have the ability of spinning. Spinning means rotating like that. They spin. As they are spinning, they align themselves to an extent that they develop what you call a magnetic field or a magnetic what? Moment. Members, what makes you become paramagnetic and paired electrons? What makes you to be non-paramagnetic? That one is presence of only paired what? Electrons. Now we go to scandium and zinc. Scandium and zinc are not true transitional elements. Reason being they are not attracted by magnet. They are non-paramagnetic. Why? When you look at them, they lack unpaired what? Electrons. When you go back to their configuration, electrons in scandium and zinc rules them out from being paramagnetic. Then the second property, to simplify, it is the catalytic property. Now when you look at these transition elements, take an example, iron. We are using it in double process. Look at manganese, like manganese 4 oxide. We are using it in preparation of oxygen. Look at platinum. We are using it in many processes as acting as, like even preparing nitric acid. And look at nickel. We are using it in hydrogenation, hardening of oils to fats. So all of those ones are catalytic what? Catalytic examples. Now what makes them to become catalytic? Now we are saying that the presence of partially filled D orbital. The partially filled D orbital creates space for the reactant to bond with the atoms of a transitional what? Element to form a more reactive catalyst reactant what? Complex, or reactant catalyst what? Complex. This one speeds up the reaction because you are going to lower the activation energy now. Two, they have variable oxidation what? States. Variable oxidation states now, these ones can enable them to transfer electrons. Transferring electrons, you can catalyze the what? The reaction. So take a note of that, the partially filled D orbital. That can now create space for the bonding between the reactant and the atoms of a transitional element. This is not done by all other D block elements. Some are not doing it. You have never seen the catalyst of scandium and so on. Now, another property, they have variable oxidation states. Variable oxidation states means they have more than one. Take an example, manganese. Manganese will have oxidation state, for example, from 2 up to when you reach 7. You'll find those oxidation states there. Look at iron. You'll find iron is having iron 2, is having iron 3, and so on. Look what this is iron now. Try to look at, for example, chromium. We will find chromium 2. You find chromium 3. You find chromium 6. Those are variable oxidation what? And so on. They have many oxidation what? States. We're saying the variable oxidation states are going to be because of the presence of the empty orbitals and then the unpaired what? The unpaired electrons. We are going to take an example of DC iron. Iron is having 3d6 and is having 4s2. Now, iron, if it's going now to use valence 2, that one is when it's going to become iron 2. That is when it's going to use valence what? Valence 2. That is using electrons of 4s. Now, when it uses electrons of 4s, it means now the 4s here is going to remain now empty. Let me say the electrons of s have been used. I can even put it there power 0 because you have used them here. Now, if it's going to become iron 3, it means one of the electrons from 3d is going to be used. So you'll find that now iron 3, you are having now, you are remaining with, you are using 3 electrons. 3 how? The 2 electrons from 4s, then 1 electron from the 3d. This implies that now iron 3, our iron 3 is going to be with 3d5. But when it is having 4s powered with what? 0. Why am I powering 4s with 0? The 2 electrons which were in 4s have been used plus 1 electron from the 3d which were 6. Now they are becoming what? 5. Now, that one now the valence is becoming valence what? Valence 3 here. So this explains why you can find iron 2 and you can even find iron what? Iron 3, like that. Similarly, you can see it in others like magnesium. Then the same elements, you can only be transition if you form colored compounds. Why are they forming colored compounds? We have already said they have partially filled 3D, and then they have the ability to promote what? Electrons. When they are promoting electrons, there is what called transitions. They do what called transitions. Electrons can be promoted from the lower energy level to higher energy level. How can they promote electrons? How can they promote electrons? They promote electrons by absorbing energy. Where are they absorbing energy from? They are absorbing energy from the sun, which energy is having different wavelengths. Now, when they absorb the light, some of the light is reflected. Now, the light which is absorbed by the atom or the ion of a transitional element, not all of the light remains there. Some light is what? Reflected. Now, the reflected light is one which is going to enter our eyes, and the way as it is entering our eyes, our cones in the eyes are going to judge it based on its wavelength. If the wavelength is in the range of blue, like copper is doing, the copper compound is going to appear what? Blue. If it's in the range of green, like chromium is doing, then you are going to see green, and so on. Therefore, the idea here for colored compound, you are absorbing light, you are reflecting some light. Now, the reflected light is one which will give us the color of the compound. So that one based on promotion of electrons and presence of partially filled 3D orbital. Then they form complexes. They are forming complexes because of the vacant or the partially filled d orbital. Now, vacant, I told you there is space. This space can welcome the ligands. Remember, we have what we call the ligands. Ligands, these are chemical species having lone pairs. These ones are chemical species having lone pairs. Lone pairs of electrons are electrons just redundant, not being used. So what happens is, these ones, the vacant orbitals are going to welcome the lone pairs of what? Electrons. And the lone pairs of electrons can be good like from nitrogen. This explains why you can find ammonia combining with copper. Copper 2. Copper 2 already is having vacant orbital. Then it will welcome a lone pair of electron on nitrogen. Then you find copper forming a complex, for example. We are going to see the details of the complexes afterwards. You can find like a complex of tetraamine, copper to what? Ion or complex. Why are you forming it? Vacant orbital. Then secondly, small ionic radius. When you have a small ionic radius, remember ionic radius is simply the internuclear distance between two ions now. Distance between two ions. Take an example, sodium and chloride, the distance between their nucleus become this ionic radius. Now small ionic radius. Now small ionic radius is going to give it a very big charge density. The charge density is going to become big. Charge density, that is when you have got now charge density. Let me try to use this space here. Charge density, I'm referring to charge density. Members, charge density we are referring to the charge on the ion over the ionic what? Radius. You have a small ionic radius and you have a big charge, you have a very big charge density. The more you have a very big charge density, you can easily attract what? The ligands here. You can easily attract the ligands, which ligands can help you to form the what? Form the complex. Then lastly, another feature which makes them unique to be called transition elements, they form what you call interstitial compounds. These ones you can even call them alloys. They can form what you call alloys. Why are they forming alloys? When you look at their metallic lattice is having space, and that space can easily accommodate the small atoms like carbon, nitrogen. So you may find that they are forming alloys. You find alloy like steel, that is an alloy of iron, and many other alloys because of the metal lattices having spaces that can accommodate the small atoms. So members, our topic has been transition. Your transition, why? You are paramagnetic, you have catalytic properties, you have oxidation, you have variable oxidation state, you form colored compounds, you form complexes,